Atoms are the building blocks of our universe. They are incredibly small, but even within these tiny atoms lies a core. We call this core the nucleus. Imagine a marble at the center of a giant football stadium. That's how small the nucleus is compared to the entire atom. The discovery of the nucleus was a landmark moment in science. Ernest Rutherford, a brilliant physicist, made this discovery in 1911. His experiments with alpha particles revealed that most of an atom's mass resides in a tiny, positively charged center. This discovery revolutionized our understanding of matter. It opened up a whole new field of study nuclear physics, and it paved the way for amazing technologies from nuclear power to life-saving medical treatments. The nucleus is a fascinating and complex world. Understanding it is key to unraveling the mysteries of the universe and harnessing its power for the betterment of humanity. Let's delve deeper into this captivating realm of science. The nucleus, though tiny, is not a simple entity. It is composed of even smaller particles called nucleons. There are two main types of nucleons, protons and neutrons. Protons carry a positive electrical charge. They determine the element to which an atom belongs. For instance, an atom with 1 proton is hydrogen, while an atom with 6 protons is carbon. Neutrons, on the other hand, have no charge. They primarily contribute to the mass of the nucleus. They also play a vital role in its stability. You might be wondering, how do these particles stay together within the incredibly small space of the nucleus? The answer lies in a fundamental force of nature, the strong nuclear force. The strong force is incredibly powerful at short distances. It acts like a glue, binding protons and neutrons together, overcoming the electrostatic repulsion between the positively charged protons. This force is essential for the existence of all matter as we know it. The strong nuclear force is one of the 4 fundamental forces in the universe. The others are gravity, electromagnetism, and the weak nuclear force. While gravity is the force we experience every day, the strong force is vastly stronger. In fact, it is the strongest force known to science. However, it operates only over incredibly short distances, on the scale of the nucleus itself. Imagine the strong force as tiny springs holding the protons and neutrons together within the nucleus. These springs are incredibly stiff, requiring immense energy to stretch or break. This is why splitting an atom, as in nuclear fission, releases such a tremendous amount of energy. Understanding the complexities of the strong force is a major focus of nuclear physics. It has profound implications for our understanding of the universe, from the formation of stars to the potential for new energy sources. Section 4. Isotopes, atoms with a variable identity. We often think of atoms as having a fixed number of protons and neutrons. However, variations exist within elements. These variations are called isotopes. Isotopes are atoms of the same element that have the same number of protons, but a different number of neutrons. For example, carbon-12 and carbon-14 are both isotopes of carbon. They both have 6 protons, but carbon-12 has 6 neutrons while carbon-14 has 8. This difference in neutrons affects the stability of the nucleus. Some isotopes are stable, while others are radioactive, meaning they decay over time, emitting particles and energy. Isotopes have numerous applications in various fields. For example, carbon-14 is used in archaeology for carbon dating, while radioactive isotopes like iodine-131 are used in medicine for diagnosis and treatment. Section 5. Nuclear power, unleashing the energy within. One of the most significant applications of nuclear physics is nuclear power. This technology harnesses the immense energy stored within atomic nuclei to generate electricity. Nuclear power plants use a process called nuclear fission. In fission, a heavy nucleus, such as uranium-235, is bombarded with neutrons. This causes the nucleus to split into lighter nuclei, releasing a tremendous amount of energy in the form of heat. This heat is then used to generate steam, which drives turbines to produce electricity. Nuclear power is a carbon-free energy source, meaning it does not contribute to greenhouse gas emissions. However, nuclear power also presents challenges, such as the disposal of radioactive waste and the risk of accidents. It is crucial to implement stringent safety measures and continue research into safer and more efficient nuclear technologies. Section 6. Nuclear medicine. Healing with radioactive isotopes. Nuclear physics has revolutionized the field of medicine, leading to life-saving diagnostic tools and treatments. Radioactive isotopes play a crucial role in nuclear medicine. One important application is medical imaging. Radioactive tracers attached to specific molecules are injected into the body. These tracers emit gamma rays, which can be detected by specialized cameras to create images of organs and tissues. This allows doctors to diagnose a wide range of conditions, from heart disease to cancer, with high precision. Radioactive isotopes are also used in radiation therapy to target and destroy cancerous cells. The use of radioactive isotopes in medicine has significantly improved diagnosis, treatment, and overall healthcare outcomes. Ongoing research continues to expand the applications of nuclear medicine, offering new hope for patients worldwide. Section 7. The Future of Nuclear Science, from Fusion Energy to Medical Miracles. Nuclear science is a constantly evolving field with immense potential for the future. One exciting frontier is nuclear fusion, the process that powers the sun. Fusion involves combining light nuclei, such as hydrogen isotopes, to create heavier ones, releasing even more energy than fission. Fusion power holds the promise of clean, safe, and nearly limitless energy. Researchers are working tirelessly to achieve sustainable fusion reactions here on Earth. Success in this endeavor would be a game-changer, addressing global energy needs and mitigating climate change. In medicine, advances in nuclear science are leading to more targeted and effective cancer therapies. Researchers are developing new radiopharmaceuticals with improved targeting capabilities and reduced side effects. Nanotechnology is also converging with nuclear medicine, enabling the development of nanoscale carriers for delivering radioactive isotopes directly to cancerous cells with pinpoint accuracy. The future of nuclear science is bright, promising groundbreaking discoveries and transformative technologies that will shape the world for generations to come.